Hello, my name is Andrew Buck. I'm from the University of Missouri, and today I'll be presenting our paper for Wiki 2020 called A Weighted Matrix Visualization for Fuzzy Measures and Integrals. So let's get started. To begin, I'm going to give a little bit of background on fuzzy measures and the Choquet integral. I'll talk a little bit about Shapley values and the interaction index. And then the main topic that I'm going to discuss today is how to visualize fuzzy measures using a weighted matrix diagram approach. And I'll give a couple different examples using various AWA operators and give a couple use cases such as multi-criteria decision making and information fusion. So to begin, we should all be pretty familiar with the concept of a fuzzy measure. Given a finite set of elements x1 through xn, a fuzzy measure is a function g that represents the value or utility of any particular subset of x, with a couple restrictions that g of the empty set is going to be equal to 0. And if we have a set A that's a subset of B, g of A is going to be less than or equal to B, g of B. So given a particular fuzzy measure definition, we can compute the Shapley value. This is a concept that originates from game theory, and it's a way of measuring the average contribution that each source makes as it's added to a particular subset. And so we can compute this value for every source and using this equation here and use that to determine how important each source is within the fuzzy measure. This can be extended to the interaction index. And in this case, we can compute the interaction, the sense of worth of any particular subset of the fuzzy measure. So when the interaction of a particular subset is greater than 0, we say that there's positive synergy between those elements. When the interaction is less than 0, we say that those elements are redundant. We also have the idea of a fuzzy integral. So if we have data, h is a function over x that maps every element in x to value between 0 and 1. So given a particular data sample h and our fuzzy measure g, we can compute the Choquet integral by sorting the elements of the data h from largest to smallest. And depending on which sources those elements correspond to, we get a sequence then of subsets that corresponds to a particular sequence of elements in our fuzzy measure. A single data sample will only produce an output for n of the 2 to the n possible subsets. So for fuzzy integral use cases, looking and making sure that you have adequate data coverage can be really important. So let's get on to the main topic at hand. How do we actually visualize a fuzzy measure? So suppose that we have a fuzzy measure G defined over a set of 3 elements, just for this example. I'm going to show it here in this table. This is the fuzzy measure that we're trying to visualize. We're going to start by creating a binary indicator matrix where every row corresponds to a different element from the set, and every column is a different subset of elements. So we start with the empty set, we add the singletons, we add the sets with 2 elements, and then finally the full complete set of all 3. So the first thing we're going to do is we're going to modify the width of every column to be proportional to the fuzzy measure value of that particular subset A. So here we've just taken the values in this table, we've applied them to the widths of each column, and you can see that as we move to the right, as we get a more complete subset of the complete full set, the widths increase, showing increased value. So to make this a little more clear what's going on, we're going to separate the diagram into separate parts for each cardinality set. So within each little block here, we're going to look at just singleton elements. We're going to look at just sets that have 2 elements, and then finally the full set. So if we had more than 3 elements, we'd divide that up even more into more different subsets. And within each one of these, we sort from smallest to largest by increasing value. So as we move towards the right within each of these subsets, the darkened areas show us which sources contribute the most, are most important. Now we can actually extend this to this concept of the Shapley Index. And Within each of these blocks, we can actually highlight precisely how much each source contributes to that particular subset. So for instance, if we look at the subset x2 and x3 shown by this column here, it has a value of zero 0.4, and we might be interested to know how much of that is contributed by x2 and how much is contributed by x3. So if we go back to the singleton and we look at the sets where we only have one or the other, we see that when we only had x3, we were already at 0.4. So adding x2 to x3 doesn't really add anything. So we have no uh, additional increase. And so there's no black bar here. Whereas the opposite, x2 is zero 0.2, including x3 in the set with x2, increase the value from 0.2 to 0.4. So we have a 0.2 increase. And so we have a black bar that shows a 0.2 increase. And so we apply this to the entire diagram. So every block here shows the incremental contribution of that source within each subset. And what we get then is black bars that are larger where particular sources are contributing more to those given subsets. Now we can go a step further and compute the Shapley Index for every source. Those are shown here on the right side. And then we actually can scale each row by that value. So now wider rows correspond to larger Shapley values. And the amount of black that you see from these black bars is proportional to that value. And so we get a sense of which sources are actually the most important in this measure. Finally, we can go a step further again and include the full interaction index as a bar graph below the diagram. So since this is a extension of the Shapley index, the interaction index for the singletons are actually going to be equal to the Shapley values here. But higher order values of the interaction index for larger subsets are shown in this diagram here. We can see that positive values in red show positive synergy between the elements, and negative values in blue show redundancy, like we saw in this example. If we have a particular data set, we might be interested in learning a fuzzy measure from that data set. So here's an example with 5 data points that we might be interested in using with this fuzzy measure. So if we were to evaluate the Choquet integral for each of these data points, we would end up sorting them from largest to smallest. And you can see that when we do that, we get these different permutations of the data. And we can visualize this using a lattice diagram where we start with the empty set at the bottom, we work our way up to the full set. So we have first row is just singleton elements, the second row is subsets with 2 elements. And every one of these data points is then a walk through this diagram that shows which subsets were activated. This is a nice way of visualizing where our data is being utilized in the fuzzy measure. And we can actually take this idea and extend it and apply it to our matrix diagram. So we can actually create a histogram then of the data coverage, add it to the top of the diagram. It looks kind of like this. So within each subset, we actually normalize so that we see which subsets were visited the most within each cardinality class. And we plot a horizontal line here just to show the average value within each cardinality set. Values that extend above that mean are darkened, and that's just a technique that helps highlight outliers, things that really extend above the average. So here's a couple examples of how this measure looks on some fuzzy measures. So here's 2 extremes, the min and max case. The min case, you can see all of the value has been shifted to the very end, the full and complete set, whereas in the max, all of the value, all the black area is right at the front for the singletons. And remember, as we sort the values of the data from largest to smallest, this means that the min is only going to look at the very last value. The max is only going to look at the very first value when it computes that aggregation. Here's what the mean and median look like. The mean, we notice all uniform black bars, so every grid cell here that has some contribution, has a uniform contribution. It's all very uniform. Vertical stripes is a characteristic of the mean pattern. And for the median, similar to the min and max, we actually have all of that value on not the first or the last, but the middle cardinality set in this case. So here's some examples that might be a little bit more realistic. First, we have the idea of an additive fuzzy measure. This is the case where if we combine two subsets, their value is the sum of the individual subsets. So there's not really any interaction happening between individual elements. And you can see in this case, our interaction index is completely zero after that first singleton case. So that's a way to identify additive fuzzy measures. And on the right here, I'm showing an example where we have a single dominant source. So X1 here is clearly the most dominant source in this measure. And we can see that it has a much wider row. It's contributing those black in each of these cells. So that's a way that we can tell that it's most dominant. This is an example from multi-criteria decision making. We have 4 different criteria that we're trying to evaluate with this fuzzy measure. You can see that X4 here is perhaps the most important of these criteria. It's the widest, it has black the whole way through. Some other things that are a little less apparent to pick out from just looking at the numbers here in the table on the left. X3 is least important, but it doesn't actually have any significant contributions until the final complete set. So there's lots of little details that you can pick into when you really examine this. It can help show how individual elements or criteria interact with one another. Here's an example that uses an embedded AWA operator. In this case, sets with cardinality 2 and 3 are fixed at 0.4 and 0.7 respectively, and the other values are chosen randomly. And we can identify that this is occurring by these vertical stripes that appear in the diagram. That's a good indication that we're getting uniform contributions from all of the sources. So as you start to look at these and compare how these diagrams look for different types of operators, you can start to pick out these patterns and see what's really happening. Last example I'm going to show here, this is a measure that was learned from data. So there were 7 neural networks that were being used to aggregate data. On the right here, you can see the fuzzy measure that was learned, the data flow through this fuzzy measure lattice. It appears that most of those individual subsets are being used. When we plot it with our diagram here, it becomes clear that, first of all, only a single pathway is really being represented. And most of this measure is being pushed to the very end. So that's characteristic of a min operator. And we see a lot of uniformity. That's pretty characteristic of trying to fuse a lot of strong classifiers together. So that's something that we can identify with this visualization approach. That's the conclusion that I have. So this is a visualization idea that is kind of an interesting way of looking at fuzzy measures in general. It might help understand what's going on between elements, how they interact. It can help you decide if you really need the full power of using a fuzzy integral or if you can use a simpler operator like an ordered weighted average. It does extend to an arbitrary number of sources, but the interpretability starts to fall off. So it might be possible to utilize an interactive version going forward in the future. If you're interested in this, the code is available on CodeOcean, so go check it out. It's fun to play with. So thank you for your time. Thank you.